Let R be the region in the first quadrant bounded by the x-axis and the graphs of y equals the natural log of x and y equals 5 minus x as shown in the figure. And our first question is to find the area of that region R. So first thing we want to do is recognize that really this area R right here is the sum of two different regions, kind of separated by this line right there. So this function on the left, that's our y equals natural log of x, and over on the right here, that's our y equals 5 minus x. So the easiest way to find that area is to find the integral from 1 to whatever this line is of natural log of x, and then from that line to 5 for y equals 5 minus x. So in order to find what this line is right here, we're really just looking to see what that intersection point is. And since you have a calculator, you can just put these functions both in, graph them, and that gives us an intersection of our x value is going to be, and this will vary a little bit depending on how much you round or where you choose to round. So 3.69344, that's our x value, and then our y value is 1.30656. Okay. Now I'm going to do this in terms of x. In other words, with respect to x, you could actually do this with respect to y, and we're actually going to need to do that for a later part of the problem. But for now, we're really just looking for the x value where our functions intersect there. Okay, so then all I need to do is I'm going to take my first integral from 1 to my line right here, which is 3.69344. So I'll do that. And that is going to be of natural log of x with respect to x. And then I'm going to go ahead and add the integral from, now we need this section over here. So we're going to, our lower bound is going to be 3.69344. And upper bound is going to be 5. And that's going to be of 5 minus x with respect to x. So when I do that, my first integral, I'm going to get a value of, again, this will vary depending on how much you rounded your bound there. So 2.13225. And our second integral is going to have a value of 0.85355. I add those together, and the region R under the curve there is going to be equal to about 2.9858. All right, part B. Region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Write, but do not evaluate, an expression involving one or more integrals that gives the volume of the solid. Okay, so on this one, we are still looking at the same region as before, right here. So what this question is really saying is that we're going to take this region and kind of treat it as if it's the base or the bottom of a solid figure. And it can be a little tricky to visualize, but once you visualize it, the integral kind of makes sense. And I'm going to do my best to draw this, but I'll admit it's not my strength to draw in 3 dimensions. So we're looking for perpendicular cross sections that are made up of squares. So essentially, I could say I need a length and a width that are the same, have the same measurements. So let's say I had something right here. Let's say that's the length of my square, just of one of my squares, because this is going to be made up of multiple squares, all with dx. Okay, so that is my length is perpendicular to my x-axis, and you kind of have to imagine less a square and more kind of a prism, rectangular prism with a square base. So let me try to draw this. Okay. So essentially we have to kind of rotate the graph in our minds and think about the square cross section coming up sort of off the graph in the z direction, I guess, in the 3rd dimension. So this right here, this cross section is that's our square, and it's going to have a length and a width that's the same as whatever our equation, whatever our function is right here. The width, now I drew this in kind of an exaggerated way, but this width right here is really approaching 0. It has a width of dx, because we are going to have to integrate to find this. So we are going to still have to remember our intersection point from before. That's still really important. Okay. So our intersection was our x value. Again, it'll vary a little bit depending on how you round it. 3.69344, and let's see, 1.30656, and that's just the intersection point of y equals natural log of x and y equals 5 minus x, and that intersection is kind of hidden behind my 3D cross section right there. So we know we're going to have to do an integral, and the good thing about this is our integrals are going to have the same bounds as they did in part A. So right, because we're still kind of finding area here. I'm going to do my lower bound of 1 and upper bound of still 3.69344. Now this is where we have to kind of think about our geometry knowledge. What I'm doing to find this volume of this whole square cross-section figure that I've created, I have to add up a bunch of individual squares. I'm essentially taking this cross-section, each individual one, adding them all up. So I want to have my function here, natural log of x, but I know, right, because that represents my length, but I know that right here, my other length, that is also natural log of x, right? Same dimensions for a square. So I need to square it, just like that. And it's going to be with respect to x because our square has width dx. Then you can probably figure out where I'm going for the second part here. From 3.6344 to 5, my cross section, the length of that is going to be represented by 5 minus x. But again, because it's a square, I need to square it. And just like before, it's with respect to x because our width there is dx. And because you don't have to evaluate the integral, this is going to be your answer right here. So part C, the horizontal line y equals k divides region R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. All right, so I have my region R under the curve, and I know from earlier, from part A, that R is equal to, let's see, 2.9858. And that might be a little bit different depending on your rounding, just like before. And we are asked to find a line that will give us half the area of this region R. So I'm actually going to get rid of that. And the question tells us the line is y equals k. So it's going to be a constant, which means we're just looking for a horizontal line. Now I don't know exactly where it's going to be, so I'm going to just draw kind of an approximation. We'll call this k, and I'll put it right there. And that's that illustrator. Okay, so when we look at this problem, we could approach it in terms of x. In other words, we could go through some integrals in terms of x, but if we look at this problem right here, we should notice that that's very similar to a bound. In other words, in our first problem, we had a vertical line, right? And that represented where our two functions intersected. And we ended up using that as an x bound when we took integrals with respect to x. In this case, we have a horizontal line, which means we could use this as a y bound and write our integrals with respect to y. And that's going to be a lot easier than doing it in terms of x. So if we're going to do anything with, in terms of y, we're going to have to take our original function, so y equals the natural log of x, and y equals 5 minus x. And we're just going to have to shift those over to be in terms of y. So we're going to end up with, over here, we end up with just, let's see, we end up with x equals 5 minus y, just getting x on its own. And over here, if I have natural log of x, in order to change this in terms of y, I'm going to have to kind of rewrite this. E to the y equals x, because e to the natural log of some value or variable will just get that value or variable. Just kind of inverse operations there. Okay, so now we have these in terms of y, which makes things a lot easier. So I'm looking for half of the area here. And I know that my full area is 2.9858. So I'm going to set up a little integral here. And I'm going to do this from 0 to k. Now, again, this is in terms of y, so we kind of have to think a little bit differently. And instead of thinking about under the curve this way, in other words, instead of thinking about that as under the curve, we have to think about under the curve being this way. Okay? So, what we know is that this whole area here is going to be equal to whatever my top function is. In other words, my further to the right function. It's going to be this whole area here, minus what's below my bottom function. What that means, and that might sound a little complex, but essentially we're taking this whole area and subtracting out what we don't need over here, so we can find just the area contained by those two functions. So it's going to be our top function, which before was y equals 5 minus x, but now that we are switching, so we're writing with respect to y, it's going to be 5 minus y. Same function, just different form. And I'm going to subtract my bottom function, which in this case is e to the y. Now, something to think about here is we actually could have used this, we could have written this integral to solve our very first problem back in part A. I would have written my integral as 0 to my intersecting y value, and that would have given me the whole area in there. But now we're saying 0 to some k value is going to give me half of the total area. So 1/2 of this region in here. but I actually know that area already. So we're going to replace that area with the actual area. And I'm going to rewrite my final answer as the integral from 0 to k of 5 minus y minus e to the y. And you know what? A little mistake here. Fix that. This should be with respect to y. Put that down here. And that's going to equal 1/2 of our original area, 2.9858. So half of that's going to be 1.4929. Now this is this would be an integral you could simplify a bit, and then probably using a calculator solve for k, because that's going to be our only variable remaining after we go through. But the question only asks for the equation here, and no need to evaluate. So that is our final answer right there.